Hello, today we return again with another physics problem that I'd like to solve for you and help you walk you through pretty much everything you need to understand to solve this problem. So the question asks, if there's a 28 hertz vibrator activated on one end of a 45-meter long string, the first disturbance reaches the other end of the string in 6.2 seconds. How many wavelengths will fit on the string? So usually when I do problems like these, I like to lay out everything that you know about the problem. So when you're asking about wavelengths and strings and they give you frequency, I like to lay that all out. So the wavelength, by definition, is velocity, v, divided by frequency, f. So we're given a few things here. We kind of have to work with what we have, and there's a few steps to get through to the answer. So essentially, we're given the frequency as 28 hertz. We're given the distance of the string, which is 45 meters, and we're given the time of from basically the vibration to reach one end of the string to the other end. So 6.2 seconds. So these three strings are given by the problem, and some intermediate steps that we need to figure out is the velocity that the vibration is propagating throughout the string, which is, by definition, velocity is distance over time. And then we need to subsequently find the wavelength, which we pretty much have everything we need to solve that. So the first thing I would do is find the velocity, which is distance over time. So we have 45 meters, and we have 6.2 seconds. If you take out your calculator, you have 45 divided by 6.2. So your velocity would be about 7.26 meters per second. So we'll write that down here. Put that away. Oops. Okay, it looks like it's giving me some. Oh, I'm working in a hidden layer, that's why. There we go. Let me change my pen type, color. There we go. So we're about 7.26 meters per second. So that's the velocity. So now that we have velocity, we can find the wavelength. So we're given the frequency, which is f. So we just plug in all our numbers into here. So wavelength equals velocity over frequency. So if I were to do that here, wavelength equals 7.26 divided by 28 hertz. Now, when you say hertz, I usually like to think of it as how many times per cycle. So basically, happens about 28 times per whatever unit you're using. So this wavelength, so this velocity is given in meters per second. This is given in hertz. So then your wavelength would be 7.26 divided by 28. So again, we can take that divided by 28. So then we're given 0.2. I would just round that up to 0.26. 0.26 meters. So that's the wavelength. Okay, so now that we have all the calculations, I'd like to show just a figure here. So let's just imagine this figure the red string, or the red graph kind of represents the 45 meter string. Now if there was a vibrator here, and it's basically, imagine it kind of shaking the string like that on this end. If you ever grab a rope and you kind of shake it, you see that the rope will propagate its wave. So let's just imagine this is animated and the vibration is occurring at this end. It will basically create these waves. And now visually, what the wavelength is, if you were to take any peaks, any two consecutive peaks of the wave, that would be your wavelength. So, so basically, if you start at the peaks right here, from here to there, that's the wavelength, and that would be equal across, no matter where you were to put it, as long as you're starting somewhere and you're ending right about the start of another cycle. So again, you can take that from the bottom as well, and they'll all equal the same wavelength in a perfect scenario. That's assuming no energy is lost, and it's basically propagating the whole wave consistently. So basically, we have this value that we calculated in the previous area, which was 0.26 meters. So if we were to add that here, 0.26 meters, we basically have to figure out how many of these will fit in that 45 meter string.